I'm very sorry, I forgot to press record. Don't try and do this video until you've collected one of these from me. We're doing question 7 on page 82, where you've got to find the shortest distance from A to K. So I've started using Dijkstra's algorithm. A was where I started, so it was the first place with a distance of 0. I then filled in temporary labels at all the places you can get to from A, and then I chose the shortest of those, which was B. So B is the second place I got to with a distance of 7. I now know the shortest distance to B is 7. I then fill in the distances from B to the places B is connected to. So 7 plus 25 is 32, and 7 plus 8 is 15. I've replaced that subsequently, but that's what it was to start with. So I then chose the shortest temporary label at a node I hadn't yet numbered off with all that boxing off. So I've got a 15 here, I've got a 32 there, I've got 8 here, or a 10 here. So I don't just choose from the 2 that lead from B, I choose the shortest from any of them, which was why that was the third one. So the shortest distance there is 8. So from there, 8 plus 5 is 13, which trumps the 15. So I cross out the 15 and put 13. 8 plus 9 is 17. So I now choose the shortest temporary label. I've got 32, 13, 17, 10. So that's the fourth place. I know the shortest distance from A to H is 10. Everyone's just finishing that one off. So what number have you got here, Frank, for K?
44.
If you've got 44, then you're correct. Let's just double check, and then let's see if we can work out how we can get from A to K at a distance of 44. So I boxed this one in fourth. 10 plus 5 is 15, and 10 plus 8 is 18. So I've now got to choose from these labels, so that means that D is number 5 with a distance of 13. 13 plus 14 is 27. That's the only one I can get to. So I've now got 32, 27, 15 and 18 as my unboxed in nodes. So that means that G is number 6 with a distance of 15. 15 plus 10 is 25, so that beats that one. I mean, you know, it is potentially you'd have one going backwards, but 15 plus 9 is not better than 8. Right, so 32, 25 and 18, so that means that J is the 7th one. 18 plus 17 is 35. 18 plus 11 is not shorter than 25, so that's that. So I've got to choose the shortest of 35, 25 and 32, so that's 8 with a distance of 25. 25 plus 24 is 49. 25 plus 10 is 35. Oh, that's interesting, so that's a similar distance. And 25 plus 9 is not less than 32. So I've got 32, 49 and 35, so that's 9 and 32. 32 plus 12 is 44. But that one still comes in first. 10, 35, 35 plus 9. Oh, that's 44 as well, same with that. So this means there's going to be an alternative, a number of choices for the final route, but that means that that's... So it's really important you understand that these numbers are not, you don't follow those to get the route. Those numbers are solely to make it easy to mark, so they can see you did the algorithm in the right order. That's it. But now we want to work out how we can get from A to K in 44. So you start at K and work out which one works. So 44 take away 24 is not 25, so it wasn't that way. 44 take away 12 is 32, so it could be that way, but it could also be 44 take away 9, it could also be that way. So do you just want to see if you have already done one route, see if you can work out the other route, and if you haven't done any route, see if you can work backwards to A to see if you can get one of the two correct answers. There are three answers. Yes, sorry, there are three answers. So I'm hoping you got one of those, and you would, you know, I normally tend to sort of set it out like this with the distances. And any one of those would have been just fine. So yeah, this is exactly how Google or Apple, well, I say exactly, no, I don't know whether it uses Dijkstra's, but you know, it is this sort of algorithm that your routing and your sat-nav apps will use to work out the shortest distance between two places. Now, you know, there's an extra level of complexity because you've got the fact that, you know, this road is this long length, but you can also drive faster on some roads than other roads. So that, you know, it's a little bit more complicated, but there we go. Dijkstra's algorithm is useful for finding the distance from one place to another. Page 82, question 8, you've got the template for that. I encourage you to have a go at that one in your own time. That's on the back of the template that you've just done. But the downside of Dijkstra's is that, it's got a really ridiculous name, obviously, but if you then wanted to work out the shortest distance from C to H, you'd have to start again. It'd be really useful if we had an algorithm that would sort of give you a summary of the shortest distances between any 2 points in a network. And I have good news. There is an alternative algorithm, and that algorithm is called Floyd's algorithm. Slightly less ridiculous name. And I have to say, I've never taught this before, so buckle up, it's going to be a bumpy ride. And certainly my head was aching last night when I tried to prepare this. Right, so we're going to use, and I found a mistake which wasn't helpful. So we're going, no. Right, so we're going to use, well, can't get any bigger, let's get it bigger. Right, so we're going to use Floyd's algorithm on this, this network, okay? And the good news is that I've given you the template to do this, which is here, exercise 3E, question 1. So let me do a quick sketch of the network over here. Okay, so the first thing we do are complete two tables. And you've got blanks for those two tables here and here. This first table is called a distance table. And the second table is called a route table. And the route table starts off with just the letters from the columns copied down. No, sorry. Yeah, no, I've done that one. That's okay. And I'm going to explain how this route table changes in just a minute. The distance table is a conventional, how do you get from one place to another? So the distance from P to P is irrelevant. But what we do is we don't fill in, how you can get from R to S by working out which is the shortest route. R to S isn't connected, so R to S we put an infinity symbol because it's not connected. We can get from R to S, but it's not directly connected. So the distance table is just showing you the length of the direct connections. So we always have these dashes through the middle. You'll either have a number or an infinity symbol. So using that network, do you want to fill in the distance table for, fill in the distance table. Now at the moment the distance table is symmetrical about that diagonal line, isn't it? Because none of these arcs have a direction to them. So we're saying that whatever these numbers are, there to there is 9 and there to there is 9. But it is important when we come to later questions that we decide which way we're reading the graph, and that's why I got in so much trouble preparing this last night. I was doing it in a different way to the textbook. So the textbook talks about this distance here being the distance from this place to this place. This is the first, this is the second. Now at the moment, the distance from Q to P and the distance from P to Q are the same. It's irrelevant, but it will become relevant. Right. So, there is an explanation of Floyd's algorithm in the book, which I just found made my head ache even more. So I'm using 2 examples, hopefully, to work through it. Right, what I'm going to do is, I'm now going to do one iteration of Floyd's algorithm. And to do one iteration, I'm going to focus on P. So I'm going to shade in the P column and row. And I'm going to fill those numbers in as they are from above. So no number there. 9, 5, 12. 9, 5, 12. Sorry, that's not very clear, is it? Okay, here's the crucial bit. The remainder of the table, the unshaded bit of the table, what I do is I compare the existing number, which is the shortest distance from R to Q, and I compare it with those 2 numbers added together, which is an alternative way of getting from R to Q. So what we're saying is, I'm comparing that distance with that plus that. Now, if the existing distance 3 is shorter, then it stays as it is. So I'm going to leave that as a 3. And in fact, oh yeah, no. You should be able to change a couple of numbers using that process. So just to go through that iteration, if you like. So you're comparing the number above in the same location with the sum of the two numbers from the shaded row and column. I'm going to use colour. So I'm hoping that you've replaced the infinity symbol here and here with a 17, because 12 plus 5 is 17. 12 plus 5 is 17. And what we do is to show that we've changed those numbers, you put them in little square brackets. And on the root table, you're really supposed to copy out all of this down here, but I'm not going to bother. I'm just going to say, right, I've changed this value, so I'm going to put in there the letter that I was shading in, which was P. So that's going to be a P, and that's going to be a P. And what we're saying is that to get from, sorry, I've done that in the wrong place, haven't I? P, thank you. What that's basically saying is to get from R to S, it's quicker to go through P. That's what we're saying, okay? So, right, so we've done one iteration. So an iteration, we have iteration, it's just when you're doing the same thing again and again and again. So I'm now going to shade in the Q column and row, and the numbers in that column and row, I'm just going to write them straight in. They don't change in this iteration. Even if there's an infinity in there, it still stays as an infinity. Okay, see what effect that has with that iteration. You should find nothing changes. Okay, so the 5 here isn't bettered by 12, the 12 here isn't bettered by 16.
3 and 7 is better than 17.
Oh, hang on. 3 and 7. It's not 3 and 7, is it? It's.
Not much.
Oh, yes, it is. Yes, you're right, sorry, that is better, isn't it? So that's now 10. Even got the answers to so what we can do is we can, so now those two numbers we changed when we were doing the P column, we're going to change them again now to Q. which now means that the shortest distance from S to R is through Q, it's not through P. Now you might be saying, well, this is ridiculous. There's only 4 nodes, I can do this manually. But you've got to remember what an algorithm does is give you something that's scalable. So, you know, once you've written a program that works for 4 nodes, it's very easy to scale it up to a program that works for, you know, 5,000 nodes, or however many nodes you have if you want to put the road network of the UK on that. Okay, so the third algorithm, well, there's going to be third iteration is shading in the R column and the R row. And then the final iteration will be shading in the S column and the S row. So just see if you can finish it off. There's not a great deal of action remaining. Is there any action remaining? I can't. Oh, hang on, I've got 5. That should be a 5, shouldn't it? Sorry, that should be a 5. So you should find you changed a couple of values during the 3rd iteration, but no values during the 4th iteration. So this is our final distance table, the shortest distance between everywhere in this network. To get from Q to S, the shortest distance is 7. Let's look at how we do the route table. So if we look at what we've changed those 2 to R and those 2 to Q. The rest are all as they were originally. So these are all P, those are all Q, those are all R, and those are all S. And the question then goes on, obviously I'm not showing the question. The question says, show that the shortest route from R to S is via Q. So this is an important step. How do we interpret the, we've now to interpret the distance table, how do we interpret the route table? So we want to get from R to S, so that tells me that I need to go through Q in order to get that shortest distance. but we haven't finished. So from R to S, I know that I have to go through Q. But what about to get from R to Q? Is that direct, or is there a... So I go from R to Q, right, no, that's direct. And what about from Q to S? So from Q to S, no, that's direct. So that shows me that the shortest distance from R to S is, I get that from the distance table, so R to S from the distance table is 10. And to get that route, you go from R to Q to S. Okay. 8 minutes. Right. We'll make a start on the second one, which is a little bit more complicated because, as you can see, you've got arrows, and what that means is there is no connection from A to B, but there is a connection from B to A. So see if you can fill in the distance table, remembering that this is the first distance place and that's the second place. I'm going to do a quick copy of the network and then I can fill in my grid as well. Oh, sorry, you've got the network for this. It's on the back of that sheet.
We have the sheet. Oh, it's clear. Sorry. I didn't even see that. Seat
Oh no, that's wrong. That's wrong. A to B is infinity. B to A is 3. A to C, so A to B, infinity, A to C is infinity. A to D is 8, so 8 doesn't have an arrow on it. C to A, D to C to B, C to D, so I'm trying. D to B, 10, D to C is 5. So this is where I got myself in a right old pickle last night, because I was going here to here, and I don't think there is a convention. Just this happens to be the way. Yeah. So it's not symmetrical anymore. It's not symmetrical anymore. And then this is just. Now, shall we just do one iteration? So the first iteration means shading in the A row and column and filling in those numbers as they are. So we've got a couple of infinities in there, which means Now actually, now you've got the table completed, the rest is pretty okay. Sorry, once you've got the initial distance table completed, the rest is okay. So just see if you can do that first iteration.
It would just be like, so with the infinity, if you just treat it the same, so the two infinities added together would not be bigger than 4.
Yes, so yeah.
So C to B,
So C to B is just going to be 4. Yeah, yeah. Infinity plus infinity is 2 times infinity. That's big. So I've made no changes. Did anyone make any changes? No. Okay. Right. I'm going to make one change in this next iteration, just to spoil it for you.
So what determines which one you're going to? Is it the sides to the top? Or
Yeah, so it's here to here. But actually, once we've filled it in, it doesn't matter. So the...
Oh, okay.
So we... So can you see which one you're going to replace?
I don't know if I'm being stupid on the first one. I thought you did it wrong or something. I don't know if I'm, like, if you go off. I don't know if I'm being stupid or whatever.
The first network. So
Yeah.
which one do you think I've done wrong?
A to B isn't. Wait, no, I've done it.
A to B you can't do.
I think I'm being stupid. Actually. Wait.
Well, no, but you're in good company, Jack, because I honestly spent hours on
No, I
this.
think it's D to B.
D to
You
B.
put it as
D to B is 10.
Yeah, no, I'm being stupid.
And whereas B to D is 6.
No, I'm being stupid.
So you should have found that the one you changed was that infinity becomes 7. Sorry, no, that's a B. The rest all stay the same. And that infinity still has to stay as infinity. So what I can do is, if you want, can I show you have you got the file answer here? So that's what you should get at the end of the fourth iteration. So I don't know if you want to take a photo of that or make a note of that. And this question doesn't ask for a route, it just asks for the shortest distance between the pairs of nodes. Question 10 in the mixed exercise is another one of these. Question 9 is a prims and crystals question. So you've got a Dijkstra's, prims and crystals, and then another Floyd. But try and finish this one off as well. I'll do it at home as well and send it to you. Yes.